Welcome to the office. We want to take a look at orbits, cycles, and the alternating groups today. So we're going to start off with just taking a look at orbits, essentially, which are produced from an equivalence relation. So let's take a look at the equivalence relation that we would like to take a look at. All right, so let's say we have a permutation sigma, which permutes elements of the set A. Sigma induces, so that was supposed to be sigma here. Sigma induces a partition of the set A under the equivalence relation. So it's an equivalence relation that we're interested in. A is related to B if B is equal to sigma to the nth power of A, right? Run A through sigma n times, and you get B out of it, right? That's kind of what we're looking for there. All right, that's exactly what we're looking for there. We want to recognize that this is indeed an equivalence relation. So you might have to think back to some prior content, either earlier in this course or a different class. So what is an equivalence relation? So an equivalence relation is a relation that is, so let's see here. We want three characteristics. We want it to be reflexive, symmetric, and transitive. And once we have an equivalence relation, all the things that are related to one another create an equivalence class. And then all of the equivalence classes together form a partition of the set. Okay, so that's what we're going for. All I want to do for the rest of this video is demonstrate that indeed sigma does induce an equivalence relation. So this is what I want to observe here. I want to first observe, let's see here. I first want to observe the reflexive nature. So I want to verify that indeed we have that the relation is reflexive. So let A be an element of A and consider sigma to the 0th power, right? When we want to look at what's generated by an element of a group, okay, what's generated by sigma, right? Our collection of permutations form a group. So we're looking at what's generated by sigma. So we can look at sigma to the 0th power, first power, second power, or negative first, second, negative second, and so on. So sigma 0 of A, but that's just the identity permutation of A, which gives us back what we started with, A. Therefore, A is related to A, and R is reflexive. Okay, the equivalence relation is R, and we're defining it by sigma. Sigma is what is inducing this partition through the relation R. All right, I also want to verify symmetric. All right, let's see here. Assume, so for some A and B in A, assume that A is related to B. Then we have that sigma to the nth power of A is equal to B for some n, which is an integer. Excellent. So I guess we didn't specify that n is just some integer here that we can find. All right, it's not fixed is the point. So for some A and B, assume A is related to B, then we get this relationship. And if I wanted to, I can take sigma to the negative nth power and input sigma to the nth power of A. And this would be sigma to the negative nth power of B. And of course, this is inverse functions. Sigma is a function. So the composition of inverse functions gives us back what we started with, A, which is equal to sigma to the negative nth power of B. And if we really want to get that form exactly right, we can observe that sigma to the negative nth power of B is equal to A, where negative n, of course, is still an integer. Therefore, we have that B is related to A, and R is reflexive. Yes. Excellent. So we have, oh, I'm sorry, I said reflexive and I wanted symmetric there. My apologies. We already had reflexive. There we go. Excellent. So we have reflexive, we have symmetric. Now we just need to demonstrate transitivity. So transitivity. Transitivity means that if A is related to B, B is related to C, then we have that A is also related to C. So assume that A, B, and C are in the set A such that A is related to B and B is related to C. All right, this is not too bad now. Since A is related to B, we have, see here, sigma to the n of A is equal to B for some n, which is an integer. And since B is related to C, we can say that sigma to the m, right? I got to pick a different number there. M and n could be the same, but we're not guaranteed that they are. Sigma to the mth power of B is equal to, I'm sorry, not A, but C rather, for some m, which is an integer. Excellent. Now what I can do is I can compose these functions together. Okay, if I were to take, let's see here, I can recognize that B is sigma to the nth power of A, then sigma to the nth power of, I'm sorry, nth power of B, but B is sigma to the nth power of A, is equal to C here. And we can work with composition. So using our appropriate notation in our set of permutations, or our group of permutations rather, this would be sigma to the, oh, let's see here, m plus n, no, m times n is what I want here. Sigma to the m times n, because I'm taking this thing and running it through m times. So n once, n twice, n 3 times, and so on, of A is equal to C. Since m times n, of course, is still an integer, we get that A is related to C and R is transitive. Excellent. Thus, R is an equivalence relation. Now, again, the importance of R being an equivalence relation is that the equivalence classes of R define a partition of A. Okay, so that's some prior content that we talked about that's making an appearance here. So for an equivalence relation, we have equivalence classes. That collection of equivalence classes defines a partition on the set. And so we say in this case that since sigma defines the equivalence relation, that it is sigma that is inducing a partition on the set A. Excellent. So we're going to go ahead and take a look at an example. We'll take a specific sigma and find the partition of the set A, and talk about what those are called a little bit more. So yes, I'll see you back here in the office in just a little bit.